Hello everybody, welcome to another video lesson. We are continuing our introduction to vectors with this lesson, but our objective here is to be able to multiply vectors by a scalar, and then we're going to do what's called resolving vectors into rectangular components, okay? And then we're going to use all of that knowledge in some real world applications, okay? So let's go ahead and get right into our concept, multiplying vectors by a scalar. All right, so if we have a vector v multiplied by a scalar k, right, we have a new magnitude that's going to be k, absolute value of k, times the magnitude of vector v, okay? And our resulting vector, we can tell the direction based off of k itself, okay? If k is greater than 0, then k times v is the same direction as v, all right? And if k is less than 0, then our resulting vector has the opposite direction as v. So if I have vector v here, and I were to say, okay, let's multiply that by 3, all right, 3 is our scalar, it's going to look something like this, okay? It's going to be 3 times the size, the magnitude of vector v, and you can see if I have these additional 2 reference vectors here, then we can see that it is in fact 3 times the length of v, all right? Now again, if I have v, and we multiply that by negative k, okay, or negative 3, it's going to be the same length, right, as 3v, but it is going to be going in the opposite direction. Okay, so something to keep in mind there. Okay, so that is our concept. Let's get right into our operations with vectors then. If we have 3 vectors in this first example, we have a minus c plus 2b. Now again, when you see minus a vector here, okay, you want to think about that as adding the opposite. We are going to add the opposite of c, and the opposite of c is going to just be the opposite direction, right? It's going to kind of flip 180 degrees, if you want to think of it that way. Okay, but same magnitude, right? Same magnitude there. So if I start with a, and we subtract, or sorry, if we add the opposite c, it's going to look like that. Okay, we're just going to go tip to tail. Then we're going to go tip to tail with 2b. But what is 2b? Well, we'll use another reference vector here, and we're just going to double b's size. Okay, I'm going to double b's size, and we get this new vector 2b here. So again, we're just going to add that by going tip to tail here with c. And now I got to think, okay, what is my initial point? Initial point is going to be the initial point of A, and then my terminal point is going to be this terminal point of 2b. So my resultant vector will look something like this. All right. Second example here, okay, I've got vector m and vector p, and we are going to find m minus 1/4 p. So 1/4 would be our k value, right? This is k times p, where k is our scalar, right? So I need to take vector p, and we're going to divide this into 4 smaller vectors. Okay, so we've got some reference vectors here. So each one of these reference vectors is 1/4 of our larger vector p. So again, this is going to be 1/4 p, but we actually want to think of this as adding, right, m plus the opposite 1/4 p. So I need to find what's the opposite of one of these reference vectors here. It's going to be that same magnitude, just going in the opposite direction. So this, in fact, is going to be our 1/4 p that we're going to add here. So we will start with m, and we will go tip to tail with opposite 1/4 p, just adding that there. And our resultant vector is going to look something like this in black here. Okay. All right, let's get into some applications here. Okay, we have Anne swimming due east at a speed of 3.5 feet per second across a river directly towards the opposite bank. At the same time, the current of the river is carrying her due south at a rate of 2 feet per second. Find Anne's speed and direction relative to the shore. So we've got 3.5 feet per second. We've got 2 feet per second. She is swimming due east, and the river is taking her due south, okay? So let's go ahead and start making some vectors here to represent this. So due east, we have our direction bearings here, northeast, southwest. Due east is going to be just heading straight east. Okay, so we'll say vector S for swimming is going to be due east here, and that's going to be 3.5 feet per second. And then we have this vector C, we're going to call it C for current, okay, and that is taking her due south. All right, so our river is flowing south, our swimmer is swimming east like that, okay? All right, so we just need to go tip to tail here. Okay, we're going to add these to figure out what her speed and direction relative to the shore is. Okay, so we'll go ahead and go tip to tail here. So I'm just going to move this vector C over to the tip of vector S, and our resultant vector looks like this, okay? Now, our magnitude of S we're saying is 3.5 feet per second. Our magnitude of C is going to be 2 feet per second. So using our Pythagorean theorem, we should be able to find the magnitude of our resultant vector, right? Okay, so that is going to be, resultant vector will just be square root of magnitude of S squared plus magnitude of C squared, right? That's just our Pythagorean theorem right there. Okay, so that's going to be square root of 3.5 squared plus 2 squared. That is going to give us a resultant vector of 4.03 feet per second. All right, feet per second there. Don't forget your units, guys, when you're working with these vectors and our magnitudes. We want to know exactly what this magnitude means, okay? We want to have some sort of context to it, all right? Okay, and taking a look at our direction now. So I'm going to give this angle here, I'm going to call that theta, okay? Because we have this right triangle here, right? Got this right triangle, which is nice. We can use some of our trig identities here, and we're going to go ahead and use tangent, because tangent is going to be our opposite over adjacent, right? So that's opposite over adjacent. And we can go ahead and take the inverse tangent of both sides, and we'll find that theta is just under 30 degrees. Okay, but we are asked the direction relative to the shore. Relative to the shore, that's important to notice, right? So this is actually not the direction relative to the shore. Okay, the direction relative to the shore, we can think of it, the river is flowing south, right? So the shore is going to be sort of on this north-south line, all right? So we're going to go ahead and call this angle phi here, and phi is going to be 90 degrees minus theta. Okay, hopefully you can see that. All right, so we can go ahead and say that we have a phi of 60.25 degrees. And I don't want to just leave it like this, okay? Because we're working with bearings and directions here, we're going to think, hey, how can I represent this 60.25 as a quadrant bearing? You guys remember how to do that, hopefully from our last video. So our quadrant bearing, we start either on the north or south line, and then we go either east or west, so counterclockwise or clockwise, okay? So here we're going to start on our south line, and we're going to go 60.25 degrees east, okay? So hopefully you remember how to write that. That would be 60.25 degrees due east from south, okay? That's how we would represent that final bearing there. Okay, looking at our rectangular components. So rectangular components are very similar to what we just did, but sort of in reverse here. So if I have this vector P, right, our rectangular components are going to be just sort of breaking this up. It's similar to like our parametric equations, right? I have some sort of representation in the x direction, right, or in a horizontal direction, and then I have another representation in the y direction, right? So we're really just breaking this up into an x and a y component. Those are our rectangular components here, okay? So that's what we're doing here when we're asked to find horizontal and vertical components. Okay, those are our rectangular components that we're looking for. Okay. All right, so we have a football player kicks a ball so that it leaves the ground with a velocity of 44 feet per second at an angle of 33 degrees to the ground, or with the ground. And we're asked to find the horizontal and vertical components of the velocity. So this is our ball here, and it's getting kicked at this angle of 33 degrees with the horizontal with the ground. And our magnitude here of force is going to be, or sorry, just our magnitude is going to be 44 feet per second, okay? So that's our velocity of the ball being kicked, okay? So we need to, again, find the horizontal and vertical components. It's going to look like this, right? And you'll notice every time we're going to develop a right triangle when we do this, which is nice because we know a bunch of trig identities that can help us learn a lot about what's going on here, okay? So here I have my horizontal component, and then this is going to be my vertical component right here, right? So using our trig identities, okay, I can say that cosine of 33 degrees, cosine is going to be adjacent over hypotenuse, right? So my adjacent here is my horizontal component, right? This horizontal component is what I'm going to call HC, horizontal component, over 44, right? 44 feet per second is what that is, okay? Now, if I go ahead and solve that for the horizontal component, all I have to do is multiply by 44. So I got my horizontal component is equal to 44 feet per second times cosine 33 degrees. And if I plug that into a calculator, I get approximately 36.902 feet per second. That's my horizontal component of this ball and its velocity, all right? Okay, similarly, I can set up an equation that says sine of 33 degrees, again, using this 33, this angle right here, it's going to be opposite over hypotenuse. Our opposite is going to be this vertical component, right? This is VC right here. Okay, so I got VC over our hypotenuse of 44, again, feet per second. And if I solve that for VC, I just multiply both sides by 44 feet per second, plug that into a calculator, and I get that the vertical component is approximately 23.964 feet per second, okay? So that's all we're doing when we are finding rectangular components. We're just looking at the horizontal and the vertical that make up this entire vector, okay? It's like what components make up this separate vector here, okay? All right, last example here, we're going to look at some tension, okay? So this is some real world applicability here. All right, we have two cables. We've got this tension T plus T1 and T2, okay? And they're tied together to support this 2,500 pound load, okay? So we've got this load here, 2,500 pounds, right? And it's at equilibrium. We have to understand what that means, okay? Equilibrium means it's not moving, right? Equilibrium means this thing is static, okay? It's not like it's swaying. It's not like it's going up or down. It's just sitting there, okay? And we're going to need to know that for later on. So you can see here, I have written the vertical and horizontal components for T1, okay? And I wrote them going up, right? Because if my load here is pulling down, right, then my tension is going to be pulling up in some way, right? It's going to be pulling this way, okay, to keep this load from being hung in the air, okay? From hanging in the air is what we're doing. So let's see, we're asked to write expressions to represent the horizontal and vertical components of T1 and T2. So we have horizontal of T1 and vertical of T1, and we know that this is going to be 180 degrees total. So that minus this 115 gives me an angle right here of 65 degrees. And then here I've got horizontal component of T2 and vertical component of T2 again. And if we were looking for this angle right here, hopefully you guys remember this situation here. We got two parallel lines with the line running in between them. That's what we're working with here. If I kind of extend this line a little bit and extend this out, right? I've got these two horizontal lines and then this line coming in at an angle, right? So I know that this angle here is 45 degrees. So that tells me that this one is 35 degrees, which lets me know that on the bottom side here, this angle is going to be 35 degrees, which is this angle right there that we're looking for. So perfect. So that's going to be 35 degrees. Now we're going to draw what is called a free body diagram. Okay, so we're just going to clean this up a little bit. That's what we're doing. And we can kind of look at this in terms of all of our forces that we have going on. Okay, so for our T1, again, I'm going to write in our horizontal and our vertical components, and the same for T2. Okay, so we can kind of label everything. So I've got horizontal T2, vertical, horizontal, vertical, and now I've got my angles, all right? And let's see, we've got this load here of This load, we can call this L. Okay, that's going to be what? That's our 2,500 pounds. Okay, 2,500 pounds. It's sitting at equilibrium. All right. Okay, so now writing our expressions to represent the horizontal and vertical components, we can just do that using this free body diagram that we have, right? Because I know that cosine of this 65 degrees, that's going to be, let's see, adjacent over hypotenuse. So that's going to be the horizontal component of T1 times the total tension vector of T1. And when I solve for horizontal component of T1, that's going to be T1 times cosine of 65 degrees. And I can use the same thinking to find the equation for the vertical component of T1 as well. Now looking over here at our green components, okay, the sine of 35 degrees, well, that's going to be opposite, which is the vertical component of T2 over this hypotenuse, which will be T2 itself. Okay, and if I solve that for V2, we get tension 2 sine of 35 degrees. And if I use the same method of thinking for the horizontal component, I get T2 times the cosine of 35 degrees, right? Now, since this is in equilibrium, okay, I know that my horizontal components are going to equal each other because this thing is not moving left or right. Okay, this thing is sitting right here. This load is just sitting, not moving. It's not going left or right at all, which tells me that my horizontal components of my tension are going to be equal to each other. Okay, so HT1 is equal to the horizontal component of T2. So we can go ahead and use these equations that we just found, and we can set those equal to each other. Okay? And then I also know that because it's not moving, it's not going up or down at all, I know that the vertical components of my tension is going to be equal to the load that we have, that's 2,500 degrees or 2,500 pounds. Okay, 2,500 pounds. All right, so I have vertical component of T1 plus vertical component of T2. That's equal to 2,500. So now we can go ahead and let's see, we're going to plug in our equations here for vertical components of T1 and T2. And we know now that we have this equation, T1 sine 65 plus T2 sine 35 is equal to 2,500. Now we did that because we want to have a setup here where we have two equations, which we do, and we have two unknowns, which we do, right? We got T1 and T2. T1 and T2. Those are our two unknowns, and we have two equations, so we can in fact solve for this. So I'm going to take equation 1 first. I'm going to solve for T1. So I'm just going to divide over this cosine of 65. And then I'm going to go ahead and plug this whole thing in, okay, for T1 in this second equation right here. That's all we're doing. So I plug that in, and I get something that looks like this. Now I just have an unknown of T2. So when I solve for T2 and I plug this whole thing into a calculator, I get approximately 1,072.84 pounds. Now from here, all I got to do to find T1, because that was the total tension of T2. Keep in mind, that was the total tension of T2. And we're solving for, or we're completing B here. Okay, given that we have the equilibrium of the resultant T1 plus T2 and the vector representing the weight of the load are the equivalent vectors. Okay, so what we're saying here is what we had earlier where we said V1, VT1 plus VT2 is equal to our load of 2,500. Okay, so that's kind of the setup for B. And we are going to calculate magnitudes of T1 and T2. All right, that's what we're doing. That's this B step here. Okay, so now I just take what I have found here for T2 and I plug that right into here. And we get an equation that looks like this. And I can just plug that right into my calculator and find that T2 is going to be approximately 2,079.46 pounds. Okay? So that would be the answer for part B for this example. Okay, now part C, find the magnitudes of the horizontal and vertical components of T1 and T2. So all we're going to do, we have our equations, right, that we found on the first slide of this example. We have our total tensions that we just found last slide. All we got to do is start plugging some stuff in. Okay? So I'm plugging in my T1 into my T1 equations, and I get 878.82 pounds for the horizontal tension, and I get 1884.63 pounds for the vertical tension. And for the horizontal equations here, I get 878.82 and 615.36 pounds for the vertical component of T2. Okay, and this is T1 again and T2. And you can go ahead and verify that, right? Because these two, the horizontal components should be the same, which they are. And then my vertical components should add, right, to 2,500, right? Okay, and they do. Okay, so we are all set here. We have completed this real-world example. So that's kind of one of the more difficult situations that you might find for your vectors and your rectangular components. But with that, you guys are good to head on, and good luck with your practice.